Alright guys, so today we're going to go over your 12 parent functions, okay? These are ones that you're going to have to learn to memorize. Let's start off super basic here with what is called the identity function. This is just of the equation. Let me get a pen here. F of x is equal to x. This is called the identity function because when I plug something into it, it spits out the exact same thing. So right over here, this is going to be kind of like our x, y table, except we're going to call it our x, f of x table. I'm going to plug in values. Now, when I plug in 0, what does it spit out? The same thing, 0. When I plug in 2, what does it spit out? 2. So 0, 0 is that point right there. 2, 2 is that point right there. When I plug in -5, what does it spit out? So -5, -5. Okay, what if I plug in 3, what does it spit out? The point is, no matter what you plug in, it spits out the same thing. So all of your points are going to be kind of duplicates of themselves. And so it's going to make what, guys? What shape is this? A line. This is called your linear parent function. So f of x equals x is just this nice diagonal line. Okay? Alright, so when I say, what is f of x equals x, you go like this. On guard like that, okay? Okay, now domain, which x values is this using? Well, what do the arrows mean? Just keeps going and going and going, right? So, would anything make me divide by 0, take the square root of a negative? Nope, so then I'm just going to put negative infinity to positive infinity. Or you could put this fancy r. What does that fancy r mean? All real numbers. Okay, same with the range. This goes all y values are being used, so I'm going to put all real numbers. Okay. Checking your memory from 1.2, what are the two types of symmetry? There's odd and even. Even is reflective over the y-axis, and clearly this isn't reflective over the y-axis, right? Just choose a new seat, just not in the back, okay? So then, what is odd symmetry? Awesome, thanks, Mikhail. So if I were to rotate this 180, flip it over, it would land on itself. Does this land on itself? Good job. So this is odd symmetry. When I'm looking at increasing or decreasing, I'm just saying, is it going up or is it going down? But make sure you read it from the left. So as I'm looking from the left to the right, is it going up or down? Increasing. Is it ever not increasing? Nope. So from negative infinity to positive infinity, it is increasing, which means it's never decreasing. We've seen asymptotes. Are there any asymptotes here? Extrema just means mins or maxes. Do we have any mins or maxes? Nope. End behavior. Let's write this out. So on the left end, what is a graph approaching on the left end? Going up or down? Down. So that means it's approaching what? Thank you. So we're going to write it out like this. The limit of our function as x approaches negative infinity, this all is just fancy for on the left side, what is our graph doing? It's going down. That's all that means. What about on the right side, guys? Yeah, so I'm going to change that and say now x is approaching positive infinity. And so on the right side, our function is going up, so it's approaching positive infinity. Okay, who can tell me what bounded means? Go ahead, Hiram.
It's where you can draw a line above or below the graph.
And not hit the graph, right?
Yeah.
Can we do that here? Nope, so it's not bounded. Is it ever discontinuous at any points? Nope, I could trace this whole thing without lifting my pen, so there we go. That is your first parent function, f of x equals x, also called the identity function. All right, pretty easy, right? Let's keep keep on going. We're gonna go through 12 of these. Doesn't that sound just so fun? Alright, some of them you've seen before, like this one, quadratic function. You guys should be pros at this, right? I'm going to give you actually a 30-second head start, and I want you to graph as many key points on this as you can. If you don't remember how to do that, we'll just try plugging in values here. Plug in a value for x and f of x, okay? 30-second head start, go. Alright, let's send this one out to Kara. What were some key points you came up with as your graph in x? Oh, wait, did I even give you the parent function equation? But you should know what it is, right?
Yeah.
What is it? So this is just f of x is x squared. That's how you get a quadratic, sorry. Some people didn't. I just assumed that you guys would know quadratic is x squared because we talked about it earlier this year. Well, if you didn't, now you do. Kara, what would be some key points here if I plugged them in and then squared them? What would I get? Awesome, because 0 squared is still 0. And that point is a special point because what is that called, guys? The vertex, right? Vertex, awesome. Okay, keep going, Kara. Give me a few more. Okay. What'd you say? Sorry, I couldn't hear you.
1, 1.
Okay, so I kind of wrote that funny, didn't I? 1, 1, okay.
2, 4.
Uh-huh.
3, 9. Negative 1, 1. Or negative 1, negative 1.
Well, you're right here,
Okay,
because if you
wait.
square a negative, it's positive, okay.
And then negative 2.
And if we kind of ran out of space there, but negative 3 would be at 9, right? So when you square a negative, it gives you a positive, and that's why it looks like that. Okay, you have to be able to come up with this on your own. Can you do that? Okay, awesome. So now, domain range. Let's look at both of those one at a time. And I'm going to call on some people to help with this. So let's start off with Magdalene. Domain is our x values. Which x values are being used here? Maybe a better way to put it, are there any of the x values that are not being used? No. She's gonna say, help me out here. Allie, what did you say the domain was?
Infinity.
Yep, it's all real numbers. We're going from negative infinity to positive infinity. If we look along the x-axis, we could always look up and see values, which means all values are being used. Other way to think about it, would anything make you divide by 0 or take the square root of a negative here? Nope, so we use everything. How, what about the range? You can see that we're not using everything with the range, right? So what would that be? Uh-huh. Do we include 0? We do, good job. And then, it just goes up forever from there, right? Okay, what kind of symmetry is this, Chloe? It is even. This is like your perfect example of what an even function is, because it's reflective about the y-axis. And if you just look at its degree, it's 2, which is even, right? Okay, cool. Keep on. on going here. Okay, is this increasing or decreasing? Well, this is actually doing both. What is it doing on the left side? Decreasing until it gets to 0, and then what is it doing from there? So I'm going to say it's increasing from 0 to infinity, and then it's decreasing from negative infinity to 0. Are there any asymptotes? Nope. Extrema is going to be mins or maxes. We do have one here. What is it? 0, 0. What are we going to call that? Is it a max or a min? It's a minimum. It's a low point, right? Is it a local minimum or an absolute minimum? That's an absolute minimum. Good job, because nothing is lower than that point. And this is actually, we already said it, this is called our vertex, okay? Okay, on the left side, Isabella, Izzy, what is going on? Isabel. Is it Isabel or Isabella? I'll just call you Izzy. I'm sorry, I have it on your name, but whatever. Left side and right side, what's going on?
So it's x to
Well, if we do negative infinity here, this is the left. So what is the function doing on the left side? Is the graph going up or down on the left?
it's going down.
It's been a while. All you're doing with end behavior is you're saying, what is the graph, where is it headed to on the left side or on the right side? So if I look over here on the left side, is the graph going up or is it going down?
It's going down.
What about on the right side? It's going up on both sides, so I'll just write that as positive infinity. So as x approaches negative infinity, meaning as we go to the left side, the graph is going up. That's all that means. And then you already said on the right side, sorry, my handwriting here is not that great. It's hard to write with gloves. But it's going up as well, so it's up and up. All right, thanks, Izzy. Let's send this now to Angelina. Is this bounded? Could.
I'm shaking her head yes, so,
What does bounded mean?
um,
Hiram kind of told us we could draw a line and not hit it. Could I draw a line above this function and not hit it? No, but I could draw one below it, right? What do we call that? Bounded below. Don't just say bounded, because bounded means you can do above and below, and we're not going to do that. Is this discontinuous? Any points of discontinuity here? Nope. So we're good. Okay, now, this is kind of what I want you guys to do moving forward. But what we're going to do is not spend as much time analyzing that. I'm going to have you fill in the analyzing notes on your own. Okay? We're going to spend more time graphing it, and then maybe paying attention to the ones that make it really interesting. Okay? So this next one here, we have the cubing function. So what we just saw was a quadratic or squaring function. Any guesses what the equation of the cubing function is going to be? X cubed. Okay, I'm giving you another 30-second head start. Start plugging in x values into f of x and see what you come up with. That's the most important part. So 30 seconds, go. Alright, let's send this to Hiram. Hiram, give me some of your key points. What did you get for the cubing function?
0, 0.
0 times 0 times 0 is 0. Cool. Keep going.
1, 1.
1 times 1 times 1 is 1. Okay,
2, 8.
awesome, and that's the last one we'll see here. But guys, if I did 3, what's 3 cubed? 27, good to know. Okay, so that's where I pause. Okay, keep going, Hiram.
-1, -1.
Oh, so a negative times a negative times a negative is a negative. Okay, keep going.
-2, -8.
And what if we did -3?
-27.
Okay, there you go. So what we're going to do here is connect those dots. And this is the informal name. I call this an S-curve. I don't know if anyone else does, but that's what I call this, is an S-curve. So last June I broke my leg playing soccer, and I had to get surgery and get a metal plate in, and now guess what I have on the side of my leg? Awesome S-curve. I'm like, yes, I could show it off to my class when I wear shorts. So maybe another time. I'll show you my scar. Okay, this is the S-curve. Cool? Can you come up with those key points? Okay, I want you to turn to your neighbor, and I want you to fill in as many of these as you can in the next minute. Go. So that involves talking to somebody. And if you don't know them, say, hey, what's your name? I should keep track of only front row person. Good job, Chloe.
Yeah, wait. So if you flip it 180 every now, right? Probably. I don't know. We'll make it up. And then increasing, so it's increasing, so negative infinity to 0. And then wait, I think it's all increasing, right? Wait, no? Yes. Yeah, it is. Yeah. Okay. So wouldn't that be negative or include 0 and then union? I don't know.
Well,
No, I think it's negative. That's what I thought, but then because it doesn't start from
positive. So when you go to negative,
Okay.
positive is included. Right.
okay, so then there's yeah, and then asymptotes.
All right, let's come back here. I just want you to shout out what you guys said. Domain, what did you say? Awesome, all real numbers, right? Okay, cool. What about range? Same, all real numbers. Good. Is this even, odd, or neither? Good job. This is odd. If I flipped it over 180, it would land on itself. Is it increasing or decreasing? It's increasing, right? Because even though it kind of starts to slow down here, it just is always going up, up, up. So this is increasing from negative infinity to positive infinity, so it's never decreasing. Any asymptotes? Any extrema? Sometimes people are like, well, what about 0, 0? Well, is it a min or a max? And they're like, oh, I don't know, it's kind of neither. Well, then it's neither, okay? Okay, is it bounded? Discontinuous? Okay, what about on the right side, or left side? Let's start on the left. What's it doing on the left? What's it approaching on the left side, guys? Awesome. What about the right? Okay, there you go. Was that too hard? Do you have any questions on what I just filled in? Make sure when you graph these that you put in the key points, though, okay? It's not enough just to kind of make a squiggle. You have to have those key points, especially the 1, 1, negative 1, negative 1. All right, let's keep on going. We're going to just get through as many. We're going to get through them all, but try to make it as interesting as we can. Okay, absolute value. The equation looks like this. I need someone to tell me, what do those bars do? Go ahead, Hiram.
It makes a negative be a positive.
Good. Why does it make a negative be a positive? Does it make a positive be negative? Why not? Because it's the absolute value. It's what it does. So the absolute value, what it's telling us is it's telling us the distance something is from 0. Can you have a negative distance? No, so distance is always positive. But so if you have a positive distance, and you take the absolute value of it, it stays the same. But if it's a negative value and look at the distance, then it's going to be positive. So for example, if I start at, let's just look at 1. How far away is 1 from 0? How far away is 2 from 0? How far away is 5 from 0? So what does it start to look like here when I see 1, 1, 2, 2, 5, 5? What shape is this starting to look like? This starts to look like the identity function, right? Well, let's keep on plugging in points. What about 0? How far away is 0 from 0? Now, this is where it starts to change. What about negative 1? How far is negative 1 from 0? It's positive 1, so we change directions here. How far is negative 2 from 0? 2, and now all those negatives just became positive. And this gives us the nice V shape. All right, now, we wanted to take the time to fill this all in. We could, but I'm just going to put all this is same as x squared. You see how it basically makes the same shape as an x squared? So, yeah, I'm going to have you fill in that in on your own time, but basically it's just the same as x squared. Cool beans? Is there anyone who's going to be really disappointed if we don't take the time to fill those in? Okay, Allie. We'll all stop for Allie. No, I'm kidding. Okay, let's go to square root. We don't want to take more time with this. This is where it looks like this. F of x equals the square root of x. Who can tell me what a square root does? Because I'll be honest, you guys have gotten to a point where you see it a lot, but what does it do? It's kind of hard to put it into words. Okay, so there we go. It's the opposite of squaring. So let's talk about squaring. What does squaring do? Okay, so then what's the opposite of multiplying a number by itself? Kind of like divide it by itself. Yeah, it's kind of weird to think about it. Can I show you a cool visual that I think is cool, but maybe you're like, that's not as cool as I thought it would be. Whatever. Have I showed you what squaring means literally? Okay, so this is, imagine I have this line segment here. I'm going to call it 5, and I said I want you to square it. Well, you would say what? What does squaring do? Multiply by itself. But we're going to actually literally build a square. You've heard of Build-A-Bear. This is build a square, okay? 5 by 5. What is the area of that square? 25. So when I square a number, then I am building a square out of it and finding the area, right? Because 5 squared is 25. Okay, think backwards now. What makes a square to begin with? Say it louder. What?
It's even length.
Okay, even lengths meaning they're all the same length, right? So all the sides are the same. Plus we got 4 right angles to make sure nice 90-degree angles, okay? So when I'm saying, hey, here's my square, it has an area of 36. What would the side lengths be if they have to all be the same? Guess what you just did? You took the square root of 36. You said what number multiplies by itself to give you 36, and it's 6. So does that kind of show you the difference between square and square root? Square is you're building a square out of it. Square root, you already have the area, you're figuring out what is the side length. I don't know if that helps at all, but I think that's a good visual for it. Okay, so now, what we're going to do here is look for numbers that we can take the square root of. I want you to come up with 4 of those in the next 30 seconds.